Welcome to the lesson on wave-particle duality. Microscopic objects or objects in the quantum world exhibit either wave-like or particle-like characteristics. For example, photons can exhibit particle-like characteristics in the famous photoelectric effect experiment. In the photoelectric effect, light shining on metal knocks off individual electrons. Higher energy light knocks off electrons with more energy, not more electrons. If light were behaving like a wave, higher energy light like ultraviolet or X-ray would knock off more electrons, but it doesn't. It knocks off the same number of electrons. One photon knocks out one electron, and higher energy light knocks out the electron with more energy. It's moving faster with more energy. At other times, light exhibits a wave-like characteristic. So for example, this is the double slit experiment. If you shine light at a barrier that has two small slits that are approximately the size of the wavelength of the light, they pass through the barriers and set up an interference pattern that you can see on the far wall. Here's a laser shining through slides that have etched in them very small slits, and you can see the interference pattern that sets up on the wall. You can see the same sort of interference pattern in ripples in water. The wave-particle nature of light is summed up in just one equation if you want to find the momentum of a photon. It's P equals Planck's constant over lambda. Here's a photon moving along. Here's its wavelength, denoted lambda. If you turn the same formula around, you can solve for the wavelength of a particle. So if you just want to have lambda on one side of the equation, then it's Planck's constant over momentum. The surprising result of this is that this is not only true for microscopic objects, it's true for macroscopic ones as well. So let's look at an example. The fastest baseball pitch ever recorded was about 153 feet per second. If the mass of a baseball is about 0.32 pounds, what is the wavelength of the baseball? All right, let's pause the video and work this out. All right, here's what I got. To find wavelength, that's Planck's constant over momentum, and momentum is mass times velocity. Planck's constant is 6.62607 times 10 to the minus 34 kilogram meters squared per second. Mass is 0.145 kilograms. And velocity is 46.7 meters per second. Kilograms cancel, per second cancels, and one of these meters cancels with one of these meters. So we're left with meters on the top. And if you use your calculator, that's about 9.79 times 10 to the minus 35 meters. Hopefully you got something close to that. For comparison, the diameter of a proton is about 1.5 times 10 to the minus 18 meters. This is 17 orders of magnitude smaller than the diameter of a proton. Let's do another example. you'll set this up the same way. Okay, here's what I got. Lambda equals h over mv. H is the same. For mass, we're using 9.1 times 10 to the minus 31 kilograms. And for velocity, we're using 2.2 times 10 to the 6 meters per second. Kilograms cancel, 1 meter cancels, and per seconds cancel. Let's put that in the calculator. That's 6.62607 times 10 to the minus 34 divided by 9.1 times 10 to the minus 31 times 2.2 times 10 to the 6. That's about 3.3 times 10 to the minus 10 meters. For comparison, the diameter of a hydrogen atom is about 10 to the minus 10 meters. This is the same order of magnitude, so you would expect that electrons exhibit their wave-like properties interacting with atoms, for example, hydrogen. All right, last example. Usain Bolt can run 100 meters in 10 seconds. Let's say he weighs 200 pounds, just to use a round number. Estimate his wavelength during a 100-meter race. And now the last question. Given your answer, is the wave-like nature of Usain Bolt observable? That's the end of the lesson. Thanks for listening.